So first of all, the question why I'm giving this talk, and then the answer is very simple, because conventional electronics is coming to an end. You all know the story. Waste energy is getting too high, end of scaling. So we have to find something beyond CMOS. And the idea is simply to replace electrons, which are particles, with waves, and doing a wave-based computing. So the new paradigm is simply, let's do wave-based computing, and if we answer this question positively, then the next question will simply be, what kind of waves shall we use? And you can guess already the answer, that will be magnons. So we are talking about magnonics. So we replace the electric current with a wave, and we choose the spin waves and their quanta, the magnons now, to do wave-based computing. And my group, especially Andrei Chumak, I spent a lot of time now to show some demonstration of devices. I will present a very, very few before I go to the more advanced stuff. The question is, why spin waves? Why magnons? And here you see a list, because the wavelengths can be very small, down to nanometers, frequency even up to terahertz, so that is very favorable. You have the interference effects, which you don't have so easily with the electrons, so you can harvest interference effects. They are easily accessible. You have intrinsic nonlinearity. Already the equation of motion, the Landau-Lifshitz equation, is nonlinear, so you have an advantage over conventional optics. If you would like to do in conventional optics nonlinearity, you can only do it via a nonlinear material. You can do everything at room temperature. Today I show you only room temperature results. There's no Joule heating. People call it insulatronics. You can do wave-based computing, and that means if you mix the layout, the footprint can be much smaller. You can do an all-wave logic, and also what is technologically very important, you have by now rather good converters between magnonics and CMOS, and the entire joint field is called sometimes even Magnon spintronics, like you see here. And devices which have been shown is logic gates, simply building on interference between two branches. It's essentially a magnonic Mach-Zehnder interferometer. I will show you in my talks a directional coupler and something which builds on that. Majority gate is for a wave-based computing, the elementary gate, in addition to the NOT gate. And I will show you the Magnon transistor, where all the beauty of cavity spintronics, cavity magnonics is already built in. So let's see. Fortunately, there's not only the magnonics community that is mostly driven by physicists. There is also, I would call it a Magnon engineering community, mostly driven by electrical engineers. A very famous person is Kitun, and you see a few other references. Here is Kitun. And what they do, they simply mix the following. They assume, let's have a magnonic device. How good is the device? How good is the computing we can do with the device, without asking how does the device function? That is the work of us, the physicists. But let's just ask them what is the result. So they make all kinds of different devices. You don't need to read it all. Majority-based synthesis for nanotechnologies, non-volatile clocked spin wave nanomagnet pipelines, even up to the Magnon transistor done in my group by Andrei Chumak. And then you can ask, what is the performance? And here is the result. You cannot read the table. But what you need to read is just the last column, this one here. That is something called the area delay power product. And the only thing which you are interested in is it larger than unity. Because if it is larger than unity, it simply means if you make a device based on magnons, it is advantageous compared to conventional CMOS devices. And this figure shows it even better. So green is always a magnonic device, blue is a CMOS realization, and these numbers stay for all different kind of applications. This can be half adders, this can be full adders, this can be some gate arrays, and so on. And you see, if you really calculate it, the magnonic counterpart does better than the CMOS. So the area can be up to 3.5 smaller. Problem is the delay, because magnons propagate essentially with the velocity of sound a little bit faster. Power consumption can be 100 times lower. So there's this area delay power product, which is just a number, can be 50 to 100 times better. And I find this is a good incentive to invest more in this technology. What we do, what I'm doing today with you, is just to ask the fundamental question, will it work? Is there a fundamental barrier? I can already summarize here at this point, there is no fundamental barrier which inhibits us to look farther into Magnon-based computing. Here, this is shown where it is actually more located. We have the classical computing, that is CMOS. We have a scalar variable, even a Boolean variable. Either you have electrons or not. You have a Boolean logic building on this. We can do wave-based computing, like I was just introducing into. We have vector variables because you have a wave. A wave has an amplitude and a phase and even a direction. It has already been shown that it can be very, very advantageous for doing special tasks, data processing. For instance, we once have built a time inverter which works in the gigahertz regime, which you never ever can realize using CMOS logic. And of course, the ultimate goal, performance increases, is quantum computing, but you know also about the disadvantages of quantum computing technology. It's very complicated, low temperatures, and one is struggling a lot with a lot of effort. And here in between is even something else which I would like to address in my talk, and this I call macroscopic quantum state computing. Most what I'm showing today has been stolen from other areas in physics and brought into magnetism. For instance, this field here is very well known. Already in the 60s, 70s, IBM started to build a Josephson junction computer, which was working very well. If it was working, the technology was too hard to deal with, and the system at the end didn't make it to the market. Now we can do it again. In superconductivity, you have a macroscopic quantum state formed by the Cooper pairs, and I will show you that the magnons can also form a macroscopic quantum state that is a Bose-Einstein condensate, and it can be used for computing, so we can apply all the physics we know from the Cooper pairs. We can implement at room temperature in a magnonic environment. I'm talking about purely classical computing, and the Josephson computer is purely classical once you have made the Cooper pairs. The Cooper pair formation is a quantum mechanical process, but the rest, once you have the wave function, it is all classical wave physics which does the Josephson junction. That statement is very important. And then you can do something else in addition, and that is called quantum magnonic analogies. Again, an area borrowed from photonics, from waveguide photonics, and that has never been done in magnonics, and I show you the very first results, that indeed it can be used, and it might be even used very favorably for new applications in data processing one day. Material is YIG. I don't need to show this anymore. The point is simply that the Magnon lifetime is the largest in any known and practical magnetic materials, so we do everything with yttrium ion garnet. One experiment which we did a long time ago should just show you the power of the experimental investigations we are doing. We are using Brillouin light scattering spectroscopy, and that is nothing else than taking photons, scatter the photons inelastically from the spin waves, or in quantum mechanical language, we annihilate or we create a magnon in the scattering process, and the scattered photon carries all the information about the energy, the wave vector, and so we can do spectroscopy on the magnons. Here is one example that is a very simple prototype experiment, a YIG stripe, just a wire which acts like an antenna, so we connect it to a microwave source. The Ørsted fields here, they just exert a torque on the moments in the film. In this way, you locally create here a spin wave. The spin wave will travel, and Brillouin light scattering is an optic technique, so we can use a full optical resolution just to see how the waves propagate. We can do it stroboscopically. We can even obtain the phase information by doing some interference approach. And here is the result, the measured data. And here you see, here's the antenna, how a spin wave in a real life experiment is propagating away from the antenna. By the way, only to one direction, so we have built-in unidirectionality if we do the experiment in the right manner. And the BLS itself, as I was mentioning, incident photon scattering from a magnon, scattered photon carries information about the frequency f of the magnon and of the wave vector q of the magnon. And it shows up in an experiment like sidebands to the incoming frequency of the laser light. Most powerful, and you will see this later, is a very high dynamic range, and I think that is the real intrinsic experimental power of this experiment. So this can be done in many ways. Here you see, for instance, a classical setup. You have here in yellow, a little bit hard to see, a microwave cavity which is connected to a microwave source. So we generate spin waves here. They are detected inelastically with scattering photons in backscattering geometry, a Fabry-Perot interferometer photon detector. And then this can be done stroboscopically. So we have a time resolution of typically a nanosecond, frequency resolution given by the Fabry-Perot. And what we can do, we can change the angle of light incidence in this direction or in that direction. So we get all the wave vector information, actually with very high resolution if we wish to do so. Well, if I say we, I mean a team, and the team is in particular Andrei Chumak. He has received an ERC starting grant for doing, which is called Magnon circuits. And I think this title speaks for itself. So he's in particular responsible for making these ideas and bringing them down to the nano world. I cannot show you very much in this direction, but we are doing that. There's also Philippe Perot, a very young scientist, and Thomas Brescher. Both are here, so you can talk to them. Vitaly Vazushka, who is also here, and Alexander Sarga. And much has been done with external collaborators because most of them are theoreticians. We need a lot of theoretical support in order to understand what we are doing experimentally. And there are many PhD students, diploma students, master students behind. And here is the group, the picture of last week. So what I would like to talk about is Magnon interference logic very, very shortly. Then I will talk about nonlinear magnonics, and the example I show, because it fits so well into the scope of our workshop here, is a Magnon transistor with all the cavity stuff. I will talk about magnonic macroscopic quantum states, and then finally about quantum classical analogies, which we now can implement into magnonics. So let's try to go through this list. I mean, first of all, Magnon's spin waves are waves. And the most easiest experiment we have done a couple of years ago, 10 years ago, 15 years ago, that is simply just having two Yick stripes. Here is one and here is one. We excite synchronously Magnons, spin waves, they propagate, we pick up the signal, we do the interference here. Then we can shift locally the phase, and by just applying a DC current to these wires, and via the induced phase shift, we can look into the interference pattern. Here is the data, and you can very nicely see the high contrast between, this is an XNOR gate. If both inputs shift the phase equally, then we get a large signal because of constructive interference. Otherwise, we have destructive interference. So this was the very first device, very big, very large, millimeter size, and nowadays this is on the way to be reduced. There are more favorable devices, and the most important is, so to speak, the generic logic device of wave physics, that it's a majority gate. Nothing could be easier than that. A majority gate always has an odd number of inputs, and the output signal is just the majority of the input signal. It sounds very easy, just calculate it. Two ones, 1 0, then the output is 1, 2 zeros, and 1 1 at the input, then the output is, of course, 0. It's the most simple thing. And all you need to do is just to make a realization. Here is such a realization. You have 3 input lines. Here you see actually a real example in the lab, very, very big. So 3 input branches. So we can put in a spin wave here. We can excite a spin wave there, one here. Here's the interference region. Here we detect the signal. And then the output signal depends on the phases of the input signal. Phase 0 is logic 0. Phase pi is logic 1. As easy as that. And then we can see what happens. That is the experimental result. You see nearly no noise. We can see here the phase shift is pi, here the phase shift is pi, and you can assign it to the 8 possible input logic states, and you see the amplitude ratio here between you have the same digits here, or you have one change is just a little bit more than 3 as predicted by theory. This works remarkably well. Now, this is a typical problem you have to give to the students, and I asked them just to calculate with numerical simulation what is the output power if you have just here only one input signal, one of the 3 input signals, and they calculated it, and they calculated 19% of the intensity comes through. That is, of course, a little bit too little if you would like to daisy chain these kind of things. Doesn't work very well. But students like to play with this kind of thing, so they came up with an asymmetric geometry like you see here. And indeed, here the output is already 64% numerical simulation. But I should say, in this business, numerical simulation is 90 to 95% of the business. Of course, we have to realize these structures in the experiment. But once the numerical simulation works, that is a very reliable statement, then the experiment will work also. Okay, so logic works, classical logic works. Of course, a NOT gate is very simple. You just shift the phase. You just shift the phase by pi, and that is simply done by moving the location where you measure by half the wavelength. Let me talk about the next item, the Magnon transistor, because if you have logics, you would like to amplify. Of course, you have to define what do you mean with amplification. And the most simple kind of amplification is that what you know from a field effect transistor. A field effect transistor doesn't really amplify. That is a misunderstanding. What a field effect transistor just does, it is a valve by which you control with a low voltage or a very low current, a large current from the source to the drain. Yeah? So you just have a valve and you either close it, then no electrons can go from the source to the drain, or with very little voltage or very little current, you open the valve and then the large current can go through the device. This we have to keep in mind. Our magnonic transistor builds on a magnonic crystal. We have heard a lot about the magnonic crystal. Here is a prototype experiment, maybe the simplest magnonic crystal you can make, a YIG stripe, and then we have here just some ditches just made with a saw or with some etching process into the material. There are much more sophisticated ways to do that, but this already works very, very well. And you all know how a magnonic crystal works. So we have these grooves here. Each groove is a little reflector, very small amount. Let's say 1% of the incoming spin waves are reflected. But if you have these many grooves here, is a multi-beam interference device, then if then the conditions that n times the wavelengths of the spin waves is equal to twice the separation here, the lattice constant, then you see all the backscattered waves are coherently superimposed and all the intensity is just backscattered. Also the individual reflectivity, like in a Fabry-Perot or so, can be very, very small. What happens is, this is a backward volume mode, dispersion very schematically shown in one direction here in the opposite direction. If we have this condition, what happens that gaps open like you see here, so there are forbidden propagation bands, so we can switch actually the propagation. And if we measure the transmission from the input to the output antenna, we get this characteristic transmission curves, and all you need to notice is just the dips we can create here because of this reflection from the grooves. So that is a magnonic crystal, and if we are sitting here, there is no transmission. So now the Magnon transistor. That is a very similar device. It looks like that, again a magnonic crystal, a YIG stripe with the grooves, an input antenna, an output antenna, and another one just in the middle of the magnonic crystal. And I must say here, these antennas do not have the only function to supply some spin waves. But the spin waves could also come from somewhere else. So it can be an all-magnonic device. So they are not really the integral part. It's only there that we can inject some magnons. And if we compare it with the field effect transistors, then you see here, this we can call the source, this we can call the drain, and this would be the gate. And what happens now with this all-magnon device? We control the source-to-drain magnon flow by the magnons in the transistor's gate. And what we do is we have two kinds of magnons. We have magnons which sit at the frequency of this dips, so where transmission is forbidden. Let's call them the red magnons. And we have magnons at a slightly different frequencies. Just here where the transmission is at maximum, let's call them the blue magnons. And then we use the red magnons to control the blue magnons. How do we do this? Oh, yeah, let's make a comment here. So that is a real device. You see it's very big, a couple of centimeters. But what you need to do, you must not compare it with a modern transistor. You must compare it with the very first transistor of 1947, so this device. So this can be scaled down, and Andy Chumak, who is actually here, has already shown this can be scaled down really to the sub-micrometer scale, where, of course, functionality is much better for any integration. So how does it work? Very simple. We have the source domain magnons, the blue ones, and if nothing happens, they flow from the source to the drain contact, and everything is fine. And now what we can do, we can inject magnons, the red magnons here in the central part, and if we do so, then the red magnons cannot propagate because they are just in the gap. If they propagate, they are back reflected, forward back, and they are in a cavity. And these magnons, because the amplitude is so large, they now non-linearly interact with the blue ones, and it's for magnon scattering, and the blue magnons cannot make it anymore from the source to the drain. It's as simple as that. And if you have a certain amount here, then none of the blue magnons can arrive at the drain because they are all scattered out here. And that is so effective because we use the quality factor of the magnonic crystal here in this area just to scatter the magnons. And indeed, here's again the comparison with the field effect transistor. What we can do, we can calculate how many magnons do we need to switch the device from a state which we could call logic 1 to a state logic 0. And already in our 1947 type magnon transistor, we can switch the full current between the logic state with 10% of the gate magnons. So we have an amplification factor here of 10. Of course, 10 is not high, but there is plenty of room for further improvement. But that is not subject of my talk. All I want to show you the principle and how cavity magnonics can be used to build such devices. Other people use it. A pity that Bart van Wees wouldn't talk. This is an advertise for his talk. He has shown that the same also can happen with diffusive transport of thermal magnons. And you can build devices. Again, that is a proposal by André Čurmak. You build a Mach-Zehnder interferometer and a magnon transistor in each branch. You notice here this graph. And so you can build an XOR gate. And here's a proposal for a half adder. Actually, it does work, but it does not work well enough because you need one crossing. And for the crossing, of course, you may not have any crosstalk. I'm coming back to that because for that we have some solutions. Okay, so that is all I would call it conventional magnonics. We excite waves, we let the waves interfere, we use the intrinsic coherency of single frequency excited waves. It would be much better if we have intrinsic coherency in our problem. And that we can generate by working with a macroscopic quantum state. A macroscopic quantum state simply means you have a macroscopic entity which you can describe with a unique wave function, one single wave function. And all what matters is the amplitude, and that tells you how many particles, how many magnons you have in the system, and the phase is the order parameter of this state. So let me show how this works. This is just a spin wave like you have seen on the title page of my talk. We can describe the spin waves with the quanta, the magnons, and they have energy, momentum, they have mass, and they have, of course, spin. And what is important that we have 4 and 3 magnon scattering. If we do the conditions right, and here I would like to make a shortcut because I've talked so often about it, you only have 4 magnon scattering as the effective nonlinearity. 4 magnon scattering is very nice because it means you have 2 incoming magnons, they scatter, and 2 magnons go out, so it's 2 plus 2, so 4 magnon scattering. And the nice thing about this kind of scattering that it is particle conserving. Same thing like a classical gas, and therefore we also talk here about a magnon gas in these kinds of systems. Let me talk about Bose-Einstein condensation. If we start with a single crystal, room temperature, no external excitation, then we can look what is the quasi-particles or the magnon density as a function of energy or the frequency. These are log scales. And that is just the distribution function which you get if you evaluate the Bose-Einstein distribution function. That is a well-known Bose-Einstein distribution function. What you can add is a chemical potential. Normally, in an open system at thermal equilibrium, there is no chemical potential, so that is the curve. But you notice the chemical potential is here in the denominator in the exponential term. And if the chemical potential equals the frequency of the magnons, then this is 0, so the denominator becomes 0, and the quasi-particle density will diverge. And that is a very important fingerprint for the existence of a Bose-Einstein condensate. How can we do that? Well, for instance, we can increase the chemical potential somehow so that it equals the minimum Magnon frequency, and then the curve would look like this. So you see the divergence here, and we would, here at omega min, we would obtain a Bose-Einstein condensate. So that is a fundamental idea behind. How do we do it? Of course, a room temperature system in thermal equilibrium does not have a chemical potential, but we can close this open system simply by injecting photons. And now again, we have photon-Magnon interactions, the kind of things we have heard so often already today. This photon will decay into 2 Magnons. Here are the 2 Magnons, so these states will be very, very highly populated. And then what happens, we have the 4 Magnon scattering. The 4 Magnon scattering will thermalize these Magnons, and it will distribute the Magnons all over this area. We call this a Magnon gas, because the particle number is conserved. And then by this, the chemical potential will increase, and as a result, Bose-Einstein condensate takes place here at these points. I do not want to go through all the things. What happens is that we can describe this state with a BEC wave function. The density is given by the square of the wave function, and the phase is given by the argument. And if we are even able to imprint a phase into such a condensate, then we have a supercurrent, which is nothing else different from a diffusive current. Supercurrent is just driven by a phase, by a gradient in the phase of this BEC, of this macroscopic quantum state. And what also matters here is NC, that is just the number of Magnons in the condensate, therefore the phi. Yeah, let's look here in the thing. What is also very nice, we can manipulate such a condensate, for instance, by changing the saturation magnetization. You can change the saturation magnetization, for instance, by changing the temperature. You all know if you make something hotter, then the magnetization goes down. If the magnetization goes down, this translates into a very small frequency shift of the condensate here. That is its translation, so that is the saturation magnetization scale, that is a frequency. But this very small frequency shift is sufficient to imprint a phase here, and in this way to create a supercurrent. That is just the equation here. So the change in phase is given by the frequency, by the change in frequency times the time. And we can do so by simply putting a laser beam on the sample, so we locally heat a little bit. Then, therefore, we create a phase gradient here in between, and then a supercurrent is flowing. We had first evidence for that some time ago, about 3 to 4 years ago. But we basically were looking for how does the condensate evolve as a function of time. On a logarithmic scale, exponential decay shows up like a straight line. And if we heat it increasingly, then you see deviations. That is simply caused that now a supercurrent starts to flow, and it carries away the Magnons from the spot of heating. But that is where we have the laser for the Boltzmann light scattering experiment, and therefore we measure a decreased number. An indirect experiment. But recently we succeeded in also doing directly measuring the supercurrent. I show this in a second. Just before, so that you really can trust in it, we can model the thing with rate equations. I'm not going with you through this. Schematically is shown here. So we have pumped Magnons. They will populate the gaseous Magnon states via 4 Magnon scattering. They will go into an area. We call it NB. It's a bottom close where we expect the Bose-Einstein condensation, and then the Bose-Einstein condensation happens. What you see here in between all these terms describes the 4 Magnon scattering in all different directions. There's always interaction with the phonon bars, but the good thing is that the interaction with the phonon bars is the same for all the Magnons. So we can really separate it out. We can factorize it out, and then we can artificially remove the damping from our system. Of course, in reality, there's always finite lifetime. And now the supercurrent, I was already mentioning it, it's driven by the phase gradient in the macroscopic quantum state wave function. And we can implement it into the equations. And if we do so, just to cut it very, very short, then we can simulate what we have measured. I should mention there is only one supercurrent in one direction. We have actually two components, but if you really plot the minimum of the dispersion of all these magnons, you might notice that this red curve, so if you propagate perpendicular to the k vector, then the gradient is much higher. You see it here with green than in the other direction. So effectively, only the transverse Magnon current here is existing, is dominating, and so we only have to look into that. We can model it, and if we do so, the full lines are the model. There's only two parameters here. One is the critical number of magnons you need to form the condensate, and the other is just a scaling factor, because with BLS we can only measure relative intensities. So this works very, very remarkably well. Now, more important is non-local measurement, and for that we use now two lasers, one for the heating and the other for scanning the sample and measuring the Magnon intensities. So we heat here, and then we have the probing laser beam which goes to the tandem Fabry barometer in the BLS experiment, and with that we just scan across the sample. And if we do so as a function of position, we get different time dependencies of the population of the Bose-Einstein condensate. You see how it changes. This data becomes much more clear what it is if we resort the data. And this is shown here now. This is a movie. What you see in red here is just the temperature distribution, calculated using COMSOL and checked with a heat camera. This agrees very, very well. And this is what we measure. And you see when we switch it on, all the magnons from the center are pulled out, and they do so with some kind of shock wave, what you see here. And this shock wave is very, very interesting. First of all, what happens here? In order to understand what happens here, consider the marketplace here in Mainz, and assume it is equally populated with people, not absolutely dense, but loosely populated on a nice summer day, and suddenly someone in the middle cries, "Fire, fire!" Yeah? Then all the people starting from the middle will run away, yeah? And of course they will create a shock wave, because they hit the other people, they can't move anymore, and after a short time the central part of the marketplace is just empty, and here is a shock wave where all the people run out. I cannot find any better example how to explain it, but I think you will understand. If you look more closely into it, it's actually very, very, very interesting, because what you can do, you can plot the distance as a function of time of this peak. And you see, independent on the power we apply, the velocity, which is the slope, is the same here. And we can do some theory, and our colleagues Viktor Wolf has done it, solving the Gross-Bitaevsky equation for the dynamic behavior. And that is basically what enters. So the dispersion is important. There is dispersion, there is not diffusion. Also, it looks sometimes very similar. And what is also important is the interaction between the magnons. It's a strong repulsive interaction. Jabko from the Demokritov group has published it here in this paper. They have investigated it, and it fits very nicely to our data. You have, in fact, it's a complicated thing. You have actually two of these minima you might have seen in the rulers before. There's interaction between, and what we need to know here, there is a fairly strong repulsive interaction. And what we now can do, we can use the Bogoliubov dispersion law for small perturbations. We are talking about small perturbations here. We can evaluate it, and we find that we can describe this hump which was moving, this shock wave. It's actually nothing, it can be well described by just assigning it being a second sound, with a second sound velocity given by this expression. It's linear in dispersion, that is why we call it second sound. You can compare it, what you might know, with second sound from liquid helium, but that is a very different scenario. In liquid helium, the superfluid phase and the normal phase are very strongly coupled. Here the coupling is weak. Therefore, you cannot separate it here between a heat wave and a sound wave. But you see it works here very nice. The first sound, that is a wave in the condensate. First sound, by the way, here is a wave which propagates in the Magnon gas, so not in the condensate. Here is a fit, and you see even a slight bending here, and that has to do that in the course of propagation, because of the coupling to the phonon bars, the total density will go down, and that is reflected very nicely and can be fitted. So second sound is observed here, so we really can talk here about a Magnon fluid. There's more we want to do. Next experiment, I'd like to advertise it, is of course now going to a real Magnon Josephson scenario. Here's one experiment we are proposing. Just 2 of these condensates weakly coupled with this weak linker in between. And of course, we can measure now with BLS locally what the phase is, so we can even inject the phase here because the Gauss-Pitaevsky equation allows us to do that. And so I hope next time I can report about AC/DC Magnon-Josephson effect measurements. Are there other ways how to create a Magnon BEC state in YIG? Yes, it's possible. And because I was already showing some of this in the introduction, let me just show this here again. That is a Magnon quasi-particle density distribution function, so the density as a function of the energy frequency. And I've plotted it here for the 2 different temperatures. Temperature 1 is the blue curve you have seen before. Chemical potential is 0. We can heat the sample if we wish to do so. And if we would have the sample at a somewhat higher temperature, we would get this orange curve. Yeah, very boring. No Bose-Einstein condensation because thermal equilibrium, open system, no chemical potential. Now you can ask the question, what happens if I somehow manage to instantly cool down the system? Instantly. Yeah? Then you have a problem because you have too many Magnons. Because once you have cooled it down, all the shaded area are Magnons which are now in excess. It shouldn't be there because that is a Magnon distribution for the lower temperature at T-min. Yeah. So these Magnons need to go somewhere. And now you have 2 mechanisms which will help you to do that. First of all, you have damping, classical, simple Gilbert damping, which, by the way, describes effectively very well, including some things like Cherenkov scattering of Magnons or what else you might think of. But what happens with the Gilbert damping, it is more efficient for the higher frequencies because it scales with the frequency. And that means these Magnons here at the higher frequency will die out quicker. So this orange curve will approach the blue one faster for the higher frequencies than here for the lower ones. And then we have the 4 Magnon scattering. So these Magnons need to redistribute with the 4 Magnon scattering. And you can use here some concepts we have developed some time ago, which we call evaporative cooling. No time to go into the details. And as a result, if you wait a little bit, a new thermodynamic equilibrium with finite chemical potential is established. And if the chemical potential approaches the minimum frequency, then we have the green curve and we have Bose-Einstein condensation. And indeed, this works. And the experiment looks like this. You have to do instant cooling. And to translate it into reality, it simply means you have to cool it faster than the Magnon relaxation times. Yeah. And this you can do if you make everything very small. Here is YIG, 4 micrometer long, only half a micrometer wide, on a GGG substrate which has very good thermal conductivity. And here you have some contacts. You have some platinum overlayer just to heat it. You put a DC current through the platinum, and then you can heat it. And when you switch off the heating currents, the system will very rapidly cool down because of the strong coupling to the lower thermic reservoir. And then we can do Brillouin light scattering like you see schematically here. And if we do so, just see what happens. This is a spectrum, initial spectrum. And what you see here in color code is the Magnon intensities. So we see the fundamental mode. We see other modes because everything is small. So we have cavities. So we have an edge mode, even at the sides of the structure. We have the first standing spin wave, which you see here is only for the experts, but that is all understood very, very nicely. Now, what we can do, we can heat the system, and if we do so, what happens, because if you heat it, the saturation magnetization goes down, exchange interaction goes down. This mode here is very sensitive to this exchange interaction, so it just goes down. After some time, you see even not very much. Also, this mode goes down. The edge mode is very insensitive to the saturation magnetization. It's all understood, but it's nice just to see it here again. So that happens here. So the system is now at a higher temperature from 300 Kelvin, actually by 415 Kelvin. And now we switch off the current. And now the system will cool down instantly on the time scale of the Magnon timescales. And this happens. And you see, suddenly we get a lot of intensity here where the Bose-Einstein condensate is formed. And if you plot the intensity, you will actually see that is here really, to the best we can say, a Magnon BEC. So we can make macroscopic quantum states even by cooling without microwave sources, without anything. All you need to have is something which helps you to detect here the BEC state, the Magnon BEC state. Actually, you can do more. We can measure, for instance, the intensity. That is the intensity. This anomaly is well understood. And then if we switch off the current, if we cool it instantly down, we get the characteristic peak here for the condensate. So this all happens. So that is the explanation what happens here. And it all fits very nicely. We did some numerical simulation. I have no time to go into the detail, but we can reproduce this remarkably well. We can check it. Because, for instance, we can, if this is a heating pulse, we can just reduce the cooling, making it somewhat slower by changing the slope. And you see, if we do it immediately, this BEC peak disappears. And as another proof how this works. Okay, I promised at the end of my talk now to go with all this background knowledge which you now have from the preceding parts into a new field. And we call that quantum classical analogies in Magnonics. The word quantum classical analogy is borrowed. You find even books with this title. Quantum classical analogy in photonics is a book by the Raman couple. You can read it all over there. So what is the idea? First of all, let's do a first step. And that is, let's look what happens if you have two waveguides. Waveguide number 1, waveguide number 2, made from yttrium-ion garnet. Here are the parameters. So the thickness 50 nanometers, width 100 nanometers, separation 100 nanometers. These numbers are chosen fairly small just to make the numerical simulation, which has been done with μmax 3, very feasible. You can easily use larger quantities if you like. You can also use smaller quantities. The scaling behavior is pretty good. And now what you can do, you can excite only here. And then what you see is that the intensity, or the amplitude, is oscillating between waveguide number 2 and waveguide number 1, and then back to waveguide number 2, and then back to waveguide number 1. If you are from Magnonics, you might find it interesting. If you are from photonics, you would find it very boring, because the only thing we have done here is just to replace photons in coupled optical waveguides with magnons. This is a magnon waveguide system. And what you can do, simply compare it with two pendula. You know, this is a pendulum, that is a pendulum, and you know from first physics class what happens if you have two coupled pendula. The energy is transferred between pendulum number 1 and pendulum number 2, and that happens here. Actually, what is very interesting here, and I will come back to this is amplitude versus time. But this you can read, of course, amplitude versus time, but you replace essentially in a waveguide the time coordinate with the space coordinate, because this horizontal axis is a space coordinate, but if you like, you can read it like a time coordinate. That is the nice thing about the waveguides. So that is what you get from the simulation. You see how the amplitude oscillates back and forth. You see the residual damping, which has been considered here in this numerical simulation. Black is power in waveguide 2, red is power in waveguide number 1. And we can define a coupling length, and that is just the length which is needed to transfer all the energy from one waveguide to the neighboring waveguide. We can remove the damping on a computer. It's very easy. Then, of course, you have this characteristic picture, which is just the same you had for the coupled harmonic oscillators you have seen on the view graph before. Okay, and now you can, of course, do a serious job, study all the properties. For instance, you can study the coupling length as a function of the gap separation, so it increases with gap separation, which I find is very, very intuitive. You can study it as a function of the width of the waveguides, as a function of the thickness, and it decreases because then the coupling is increased with increasing thickness, or as a function of the wave number, then again it increases here. And this can be all understood in very simple terms. You can use it. You might remember in this Magnonics, Spintronics part, I was showing you already a half adder. We have the problem of making crossings. If it comes to crossings, the technologies jump in, because what the technology hates is to build bridges like this, yeah, because you have to go in the third dimension, you have to pattern many different layers, you have scattering if you use optical waveguides or magnonic waveguides. That is not very favorable. And having a direct crossing in a single plane, then of course you have leakage from one waveguide to the other. This doesn't work very well. But you can use this device as a planar crossing device. It's only one single layer which you have to pattern. And what happens is in this area here in between, what you just have seen, you can simply consider as two coupled modes. Here is one, here is the antisymmetric one, this is a symmetric one. You can plot dispersion curves, and then you have always these two modes because of the coupling here in between. And you can use that now as a crossing device for the magnons. You can even switch it very easily because, for instance, by changing the frequency, if you wish to do so. This case here, you see we switch all the intensity 99.6 in the simulation from waveguide number 1 to waveguide number 2. If we choose a somewhat different frequency, we have a half and half splitting. If we have another frequency, everything goes into the upper waveguide. And I should really point it out, there's a very talented Chinese student, Xi Wang in my group, who has done all the simulations under guidance of Andrei Chumak. And if you have more questions, just go to Andrei, who is here, and discuss it with him. So it can be done. It can be even used as a frequency multiplexer. If you have different frequencies, one frequency would only go here and the other would go there. So you see, if you think about a little bit about applications of these magnonic directional couplers, there's plenty of room just for making inventions and for improving performance of magnonic devices. So we can use it as an interconnector, as a multiplexer, and as a power divider if we wish so. Now let's go to something more, even more interesting, and that is quantum analogies. And now consider a three-level quantum system. So we leave magnonics for a moment, we go back to atom physics. Yeah. And assume you would like to make a transition from state number 1 to state number 2, but unfortunately nature forbids that because this system is laid out in a way that this transition is dipolar forbidden. But fortunately, there is a third state which you see here, so you have to take the detour over this state. And now what you can do something, you can translate it into our world, in our magnonics world, that is by replacing this device with our waveguide structure. Of course, we now need 3 different waveguides, and what we do, we replace the time in this atom physics scenario to the space coordinate, because these waves propagate all with a constant velocity, and velocity translates the time coordinate here into the space coordinate, and then we can easily measure these kind of things. And what you have here, the transitions, these are Rabi frequencies. You can excite them with a laser, for instance, and the Rabi frequency is replaced with the coupling lengths, or the reciprocal of the coupling. With the reciprocal of the coupling lengths, which we call the coupling strengths. Just the same thing, only the reciprocal value. Yeah? And for instance, this scenario we can mimic with 3 waveguides. So here is one, and if you have a wave here, we populate this state. And if you want to go to this state, that is, you see it here, and we have some intermediate state, which is just the middle state. And now you can think we just can use a directional coupler to transfer the energy from first from state number 1, then to state number 3, and then to state number 2. And here is actually there's a Hamilton operator, how this all works, and here is the state vector. So that could be done. Let's see how it works. The most easiest thing is just transfer the system from the initial state number 1 to 2. That is what we want to do. Direct transition from 1 to 2 is forbidden, so we need to pass via number 3. And that we can, for instance, do if we first apply, in this optic case, a laser pulse with a Rabi frequency omega p, the primary one, and then we bring the system to that state. And a little bit later, we just must not wait too long, because state number 3 can have a short lifetime. Then we apply a second pulse with a Rabi frequency omega s, and then we transfer the energy from that state to that state. And that is called the intuitive scheme, because it is very intuitive, isn't it? Is it the best scheme? It's not the best scheme, because there is something which works much, much better, but that is counterintuitive. and that is called the STIRAP process, the stimulated Raman adiabatic passage. And I'm very proud to present these results, not because we now have done this experiment in Magnonics, but originally the STIRAP process was found in Kaiserslautern some 30 years ago by my colleague Klaas Bergman, and he has done the very first optic STIRAP process. What he found is you transfer, first of all, this is a quantum mechanical state, and of course these Rabi frequencies or these transitions are not independent. You have to consider it as one single coherent quantum state which consists of these two transitions. So the counterintuitive scheme works different. You first apply this red transition with omega s, and then you apply a laser pulse with a blue Rabi frequency like you do here. And then the transfer is much more efficient and much more robust in particular. So minute details of the state which can fluctuate or whatever might happen to it are not anymore so important for the process. Okay, and what is very important, if you really look into the STIRAP process and the literature, you will find the transition takes place, but state number 3 is not populated. It's called so-called dark state. And now I will show you that we can realize that in Magnonics, in numerical simulation. What I was saying, numerical simulation is 95% of the entire business. Also, we have to do the experiment as the next thing. So, okay, we need this adiabatic dark state here in the middle. Let's see how it works. We have 3 waveguides. We excite the magnons either in waveguide 1 or in waveguide 2, and they propagate from the left to the right, so you can consider the horizontal axis as a time axis if you wish so. Of course, in the experiment, it's a real axis. And then we have the coupling here in between, and we can calculate the coupling constant. It's the same thing like you have seen with the directional coupler. And then for the first coupling, we have this black curve, and for the second coupling, we have this red curve. You see, they are not at identical positions, but they overlap a little bit. And that is necessary in a quantum mechanical language for an overlap of the transition wave functions. Now, let's do the intuitive scheme, and that is an analytic model which you can easily set up. You see the equations here with some rate models. And then we see initially only the blue state, the blue waveguide is populated, that is here. And finally, you put something into the black state, which is here on the other side, and also the red state is a little bit excited, and the middle, just a mass of superposition of all the states happens. If you do the same with the counterintuitive scheme, you find the following. You see the black intensity, you now excite here, and you see you hit the system after actually the non-excited waveguide number 1 comes close to waveguide number 3, but now we are able to transfer all the energy, all the amplitude from the black waveguide, so from this one here into this blue waveguide, which is this one here. And that is geometry for the setup, so everything is very easily doable in the experiment, and again, the experiment is under preparation. And here is what you see. Let's first look into the intuitive scheme. Yeah? And what you see is we excite spin waves here, they couple to the middle waveguide. The middle waveguide is pretty well excited, and you see that even some waves propagate away here, still some amplitude. If we do everything right, we get a fair amount of the amplitude into the lower waveguide, and then you see the magnons here. And now the counterintuitive thing. The counterintuitive thing is here, and you see we now excite here. We couple to the middle waveguide on the time scale after the upper waveguide has coupled to the middle waveguide, but all the intensity makes it to the upper waveguide. And no excitation in the middle, so it's really a dark state. You see some localized modes here in the middle, but definitely nothing here outside. And if you evaluate these numerical simulations, then you find the following. Again, that here is the intuitive case or the bad case, and then we see a lot of oscillations here in between. There is some numerical noise here, but you see that the intensity just goes forth and back between the two waveguides. And if we do the same thing here for the counterintuitive scheme, no excitation here in red, or nearly no excitation here of the red one here in between. So that is the opening of, I consider, an entire new field. Of course, we can go to our colleagues in photonics and see what they have done. They have done a lot of these quantum classical analogies, for instance, coherent destruction of tunneling, non-exponential decay, and Zeno effect. You can do adiabatic stabilization in ultra-strong laser fields. I showed you the STIRAP process. There are a few other ones: induced electromagnetically induced transparency, the outlet Towns effect. You can even look into problems like Bloch oscillations and Zener tunneling in these model systems, dynamic localization, Anderson localization, and so on. This all has been shown in photonics, and now it's our work to transfer that into magnonics with numerical simulations and, of course, with the experiments. And that is what I wanted to show you, and I tried to guide you a little bit through the field of modern magnonics. I showed you interference with this majority gate. I showed you the Magnon transistor, where we use cavities to enhance the amplitude to work with few magnons already in the nonlinear regime. I showed you that we can create magnonic Bose-Einstein condensates, which we can consider as macroscopic quantum states, and we call it macroscopic quantum state computing because we want to use it for functionalities. There are many proposals. I showed you the magnonic Josephson scenario, and last but not least, I showed you that we can enter the magnonic quantum classical analogy world by building the first magnonic quantum classical analogy device, which is magnonic STIRAP. And that, of course, it makes a lot of fun now to consider to use that for future applications if you would like to use it in information processing using magnons. Thank you very much for your attention.